Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, so today I am going to do, so we have been trained on this Dirac operators, bracket notation in the first half of the semester. So today I am going to show you how it is elegant to work with this ladder operator and get whatever solutions which we got earlier. You remember how we got the solutions? We tried to write the Schrodinger equation in position representation, which gives you the wave function. We look at the differential equation, then we see that it is corresponding to what special function? Hermite polynomials, and then we tried to say what is the solutions, and we also saw naturally we were getting the odd functions, even functions, because it's a symmetric potential, V of x equal to V of minus x, and we did all these things in a rigor explicitly by working out the differential equation. Now what we are going to do is, we are going to use this power of operators and try to solve in a much elegant fashion. Okay? Is the motivation fine? Okay. Okay, first of all, you need to see what are the natural scales in a given problem. Okay. So one is your familiar one, which is your energy scale. H cross omega is in joule units of, it's an energy scale. And in the harmonic oscillator, the parameters which are there are mass, frequency and H, the Planck's constant. See, these are the three constants which you have, with which you can play around and get dimensionful quantities. And can we determine a length, natural length, using these three parameters? Sure, all of you have done this dimensional analysis, right? So can you try to figure out how to play around with M, H cross and omega so that you get the dimension of that as L. H bar by M omega square, square root of that. Is that correct? M omega squared or M omega? So the dimensional analysis, if you do, H cross omega is energy, H will be energy by omega, and then omega is 1 over time, use that, M is M, and you should be able to show that the dimension of this piece is L. Okay. So why are we doing this? We would like to write, suppose we write a position operator that has length dimension, I can make it dimensionless by introducing and call it as, if you want, as some dimension. I don't know whether we need to use a tilde just to say that this is the dimension of this is dimensionless. Okay. Many times it's convenient to work with dimensionless quantity. Okay. So if you see your Boltzmann distribution, you write e to the minus beta e, right? Beta should have dimensions of energy, inverse of energy, right? So that the exponential thing becomes dimensionless. So beta is 1 by kt, and you make this, you can call this beta as some dimensionful quantity with the inverse energy, so that E by that is dimensionless. So in a similar way you can treat this to be this one to be dimensionless. Okay. Can we do a similar thing for momentum? Can we do a similar thing for momentum? Can you find a unit using h cross m omega which can give you momentum? Someone, P tilde hat will be P hat divided by root h bar m omega. So this is also dimension. This is the first motivation. If you see any books, they start dividing by these factors. It's nicer to work with dimensionless operators using the allowed parameters which are there in your given system. In the harmonic oscillator, you can play around with m and omega, and h cross of course is there in any quantum physics. It's a universal Planck's constant. Okay, so we can determine this natural length scale, I said, is h cross m omega, and you can write the dimensionless operator as hat position operator divided by this length scale. Similarly, you can write momentum operator. Okay, so this is going to be an algebra of linear operators. Okay, so this is a theoretical idea. Okay, what is the idea? We introduce two operators. Once I say introduce A and A dagger, and if I say they are different, you know that they don't correspond to observables. This is a mathematical way of doing it. We're trying to find some expectation values or anything. It is not connected to any observables in the lab. Observables are connected only to the position and momentum, but this is written for convenience. We have written this operator for convenience. The two operators, the complex conjugate of A is A dagger. You can see that plus I is the imaginary I, becomes a minus I. You know, just to make my math simpler, I have introduced your square root 2 here. Okay, so this x operator divided by h cross by m omega is dimensionless. P operator by h cross m omega is dimensionless. That is the square root 2 which is added just to make things simpler, as we will see. Okay, so these are the two operators which we are introducing, which are complex operators, and note that they are not Hermitian operators. And you can reconstruct your position operator by reworking back, rewriting the linear combinations of, and this is Hermitian. It's very clear, right? When you do dagger on this is a Hermitian operator. What will be for P? The momentum operator will involve an I factor, because when you do the dagger, it picks up a negative sign. I denominator will pick up a negative sign, so that P becomes Hermitian. Okay, please check these steps from the previous slide, that you get position operator can be written in terms of the two operators. These operators are called ladder operators. We'll come to seeing why it is called ladder operators. What is a ladder? Ladder is climbing up or climbing down on a ladder. So this operators are supposed to do by climbing up on energy eigenstates or climbing down on energy eigenstates. So that's why it is called as a ladder operators. Okay, you will see that when we do the math, that they are called the A and A daggers are called the ladder operators. So we are always going to use the position momentum commutator. Using this, can we get what is commutator between A and A dagger? Okay. So take the commutator X and P, substitute here left hand side, do the right hand side and see whether we get a commutator of A with A dagger. Okay. Can you try to work it out? IH cross, substitute here A plus A dagger and A minus A dagger. Remove all these factors out. I just substituted the X and the P. Simplify this. It becomes H cross M omega cancels, minus IH cross, IH cross, A with A is 0, A dagger with A dagger is 0. So what will the final answer be? What happens? Someone? Already a minus sign. Minus I A dagger with A. Huh? There is an extra 2? Yes. Yes. Good. So there is another 2 from. Thank you. So there will be a by 2. And this turns out to be, this is same as this one with our opposite sign. So it becomes, there is a 1 by 2 here. So that gives you A dagger, 2 cancels. I also cancels, right? Why did I keep the I? I got cancelled, I thought. I got cancelled. And this is 1. Okay. If you remember, A and A dagger were dimensionless, so I would expect this to be, right hand side should be some number, and we do get it to be 1. Okay. So this is to play around with commutator brackets. I assume that you all have been trained in the first half that you can do these things easily. Okay. So A dagger turns out to be identity. Call this to be an identity object. By the way, we know trace AB is same as trace BA. What will happen here? So it has to be a infinite dimensional vector space. You cannot have a finite dimensional vector space like angular momentum. Angular momentum, if you know that, we will write it in such a way that these matrices are always traceless. here I can't do. Trace of identity is never traceless, right? Can you make trace of identity to be 0? Impossible. So this xp I told you earlier, xp equal to IH cross implies that we are in an infinite dimensional vector space. The same thing holds for this. It's the same system anyway. Okay. So now the next exercise for you. You had the Hamiltonian, which is p squared over 2m plus half m omega squared x squared. Replace x squared by the square of this. Replace p squared by the square of this. And AA dagger is not same as A dagger A. Why? Commutator is non-zero. So you can use this commutator to write AA dagger as A dagger A plus 1. You can use that. Okay. So do that and check out whether you get Hamiltonian to be A dagger A plus half. Can you further simplify? The first two terms will cancel, right? And you can show that it is h cross omega by 2 into twice A dagger plus A dagger A. There's another 1/4. Did I miss something? So there is a I put the by 2. Oh, also there is a half. Okay, good. Can you simplify this? Use the fact that commutator of A with A dagger is 1 means A dagger is 1 plus A dagger A. Fine? So if you use this for the first term, okay, so let me cancel the 2. This can be simplified as h cross omega by 2. There will be 2 A dagger A, because this A dagger will have 1 plus A dagger A, and that 1 will also be added. So what happens finally? The 2 can cancel with this, but then you can put a half there. So I can remove this 2, but you put a half. Clear? So the Hamiltonian finally turns out, after the simplification, turns out to be, it has to be in units of h cross omega, that's also a check, dimensions of Hamiltonian, multiplied by dimensionless operators. A dagger A were all made dimensionless. A dagger A is a dimensionless operator. Is it Hermitian? A dagger A is Hermitian. A is not Hermitian. A dagger is not Hermitian. They are still linear operators, but A dagger A is Hermitian. So everything is fitting in place. Left hand side, if it has to be called as an observable, is all correctly done. Had you got A squared plus A dagger squared here, then also it is Hermitian, right? So it is only if you get some A squared separately, then you know there is a mismatch. But A squared, is it an observable? Is it Hermitian? A squared alone? A squared alone is not Hermitian. Okay, so these are ways in which you can make sure that your algebra is correct, dimensions are matching. So in all the books, you would have seen that A dagger A is called number operator. Okay, we will see why it is called as a number operator. So typically, if you say it is a number operator, it should extract the number of particles, some kind of an integer number. Okay, so then we call it to be a number operator. So we need to see why this A dagger A is called as a number operator. We will see at some point. Right now we know A dagger A is a Hermitian operator, and if suppose I can find the eigenstate of A dagger A, will it also be an eigenstate of Hamiltonian? It will be an eigenstate of Hamiltonian because the number operator commutes with the Hamiltonian, right? Number operator commutes with the Hamiltonian, so you can say that they share the same eigenstates. Okay, take an arbitrary state psi. Take an arbitrary state psi. What can we say about the matrix element? If you write psi with A as some chi, then the adjoint action will be psi with A dagger will be chi. So psi with the number operator psi is nothing but psi A dagger A on psi, which is nothing but chi with chi, and this is a norm. Norm can be positive or at most it can be 0 for a null vector. So this indirectly tells me that the expectation value of the number operator in any state cannot become negative. Suppose psi was an eigenstate of the number operator. Number operator is Hermitian. Eigenvalues have to be real. On top of it, it has to be positive. Positive or at most 0, not negative. So if suppose I find eigenstate lambda of a number operator is lambda on lambda, then this implies lambda is real and greater than or equal to 0. Both the conditions apply. Okay, so what can we say about this matrix element? As we have already worked it out now, we see that the matrix element has to be positive definite. Eigenstates of the number operator hat n, if suppose lambdas are called to be the eigenstates with eigenvalue lambda, they have to be real non-negative eigenvalues because n is Hermitian and matrix elements are positive there. So this just to say that the number operator commutes with the Hamiltonian, they will also be eigenstates of the number operator. Hamiltonian and number operator will share the same eigenstates, and eigenvalue of the Hamiltonian will be h cross omega times lambda plus half, right? Is that right? Okay. So when I write n hat on lambda to be lambda times lambda, if I try to find the matrix element of the expectation value of a particle in the state, this will give you lambda, and this has to be greater than or equal to 0, and n hat is Hermitian, which implies lambda is real, so lambda has to be non-negative real. Okay, eigenvalue. Is this clear? Now on top of it, we also say that Hamiltonian is h cross omega times hat n plus half, right? So therefore, Hamiltonian on lambda will give you h cross omega lambda plus half. Will also tell you why lambda is a number operator now, because since you know what were your eigenvalues of the harmonic oscillators involving integers which were non-negative, right, which is consistent with all these. But why integers? This condition only tells me lambda has to be real. We need to figure out why lambda has to be integers. Is that correct? I have not still proved for you that lambda is integers. I only said from this algebra, introducing the ladder operators, that lambda has to be non-negative. That's all I have said, and real. You need to still prove that lambda is integer. We'll do that.